Hi everyone, CJ Doolittle here. Thank Charlie and Ben for hosting us and getting things organized. Along with my colleagues Malhar and Roberto, I'll be talking today about GPU-native CFD solver Flow360, our contribution here. Also a young organization like Volcano, so a big team. Also a lot of thanks to the committee for helping us to stay on track in the automotive sector here. So kind of high-level overview. One thing about Flexcompute, we're similarly looking towards next generation. How can we make CFD accessible for industry practices? One thing that we like to emphasize is a lot of flexibility in our methodologies and processes and compute resources that are available to end users. So I'll talk a little bit today about both things like design explorations using steady simulations that are super fast, as well as more rigorous detailed studies in DDES related back here to scale resolving simulations. On the kind of two ends of the spectrum, we're talking about single digit to tens of minutes for these scale RANS solutions, and a few hours turnaround for the DDES results that we'll be looking at. Flexcompute as an organization is, again, really looking towards next generation solutions, focus on advanced computing and taking advantage of the wealth of an explosion actually of compute resources available worldwide. The capabilities that we all are looking at here is like multi-physics platforms, applications, ranging from things like electromagnetics here displayed at right, which we have a separate offering for, but also through the gauntlet of fluid dynamics and thermal effects that are applicable to automotive and other sectors as well. We can see here kind of like an overview of some of the things that the Flexcompute team are looking at, various different applications ranging from electric aircraft through semiconductors and cell phones, for example. Okay, so specific to Flow360 is the CFD offering. It is a finite volume, fully compressible Navier-Stokes solver, written from scratch to be entirely GPU native. Some of the applications and methods applied are a little bit unique and new maybe to the automotive sector, and we'll talk through some of those in a little bit, but there's also a lot of traditional methods that everyone will be familiar with, namely RANS solutions with K-Omega and SA turbulence models and such. We'll be showing DDES with low dissipation scheme applied here today and a novel wall model. Additionally listed at right are a number of other kind of methods that I think are relevant to the space and might be applicable to other non-workshop items of note. Flow360 is provided in a modern system and framework, and so the environment is a cloud-based system, and interaction from the user experience standpoint is via nice modern Python API, as well as a really responsive web interface that affords a lot of opportunities for collaboration and such. Okay, so jumping into some of the details. With regards to the meshes, Flow360 is a node-centered solver, which differs from the norm kind of here. And so when we were looking to the committee mesh, we wanted to stay on track as best we could in alignment with the other participants. But one challenge here is namely the boundary layer and the first wall spacing and the resultant Y+ that you get from those simulations. We see a kind of a split figure here in the middle where we're showing the committee mesh at left, where we're getting Y+ values at or above 100. And so something that we need to take into consideration if we're trying to compare apples to apples. So we took a step in trying to work through a custom mesh using ANSA. We tried to mimic refinement regions to the greatest extent possible and continue to maintain boundary layer coverage that we would have with the committee mesh. You'll see we'll carry these forward, but the committee representative mesh, I will say, increased in node count slightly at left, which is our degree of freedom that we're going to be working with, but only slightly above the 157 million cell mesh that the rest of the participants are mostly working with. And in all of these examples, when we're talking either customer or the committee, the surface mesh itself is identical. So we're starting from that and growing boundary layers on top of that. One of the first steps we took with this is with the wall modeling approach that we have implemented. It's a little bit unique, so we took the opportunity to kind of go through a study to evaluate what type of sensitivities we'd be seeing. So what we're looking at is using those custom meshes I was referencing, varying specifically the first layer height, and then balancing that with the number of layers grown to accommodate coverage of the boundary layer consistent with what the committee mesh was looking at. You can see a little bit of variation across the primary integrated load metrics, but I draw the attention to like the L1 profile where we see a nice kind of overlay of all these RAN solutions. The dashed line here is with a wall resolved application, so the wall model approach is not actually applied there. So that's where we actually start to see a little bit more significant deviation from the inevitable results, and all of that's off-body, downstream of the vehicle in the wake. Additionally, I think the only other point where Y plus type sensitivities really show up if we look at that U4 profile, specifically underbody, and so this is in the tunnel under, kind of in the center of the body of the vehicle, and it's just offset from the wheel actually. But this is a nice exercise for us to go through to kind of show that we have some pretty high level of confidence in the robustness of our wall model approach. Okay. So more on steady solution. So this is just kind of looking at the baseline. So this representative committee mesh as well as our own custom model. Very standard kind of expectations that we've seen historically with RANs, notably underbody at kind of the leading edge area as well as the rear end. We have that definite shift in pressure profile along the back end of the vehicle, all within expectations, but again, something that is a useful tool. We're getting trends right, and we're producing results here very quickly. And then stepping into kind of where we understand a lot of like industry practices, apply different techniques to maybe adjust turbulent parameters to kind of help mimic or represent or align their simulations with experimental findings, whether in-house or otherwise. So this is something where we're like intentionally modeling or modifying turbulence to help match up with the experiments to the greatest extent possible. We took a pretty one-off kind of approach here, so we're not trying to like get all those finite details out of the way, but we're modifying here in K omega SST, and we get a nice improvement on that leading edge area that I was just mentioning under the body. Apologies from aerospace, so leading edge is always the terminology I use, but then also looking at the aft of the vehicle where we're getting a definite shift up in the pressure profile there to kind of better align with experiments, thus improving our drag prediction, lift for the front and after, also adjusting slightly, maybe not always in the preferable direction, but this is the kind of thing where users can tune things a little bit and have some flexibility. Also notable here displayed is the SA model for turbulent closure and LSSA, which is termed for late separation SA model. So this is a new modified SA modeling approach that Philippe will be formally presenting at AAA SciTech in the coming months. These are just preliminary results where we wanted to show that this is an additional opportunity that end users can take advantage of. Okay, and then finally on the design deltas, this is again kind of a primary use case for RANs. You can see a good amount of influence on the wake downstream of the front tires and how much more streamlined we are going around at this particular cut plane. Also reduced influence on the downstream tires as well. Delta here also on the sidewall in terms of the pressure profile. We see a nice match overlay in the delta change from with the modification included. Both of these models have a little bit of sensitivity in terms of like the Y plus and kind of the overall resolution of mesh, but all things considered for a rapid study, this shows promising results. Okay, so stepping into scale resolving here now, we're again using DDES. We have K omega SST applied here and a low dissipation scheme. We have again the custom mesh as well as the committee representative shown, and All of these are showing some time history plots of the velocity fields as polled for the committee submissions. I guess notably at the upper right, our drag and lift results are probably not as well aligned in terms of absolute values as we'd like to see. However, we're getting trends in the right direction and all that. The velocity profiles showed a lot of promise, so we're happy to see this. L1, for example, really tracks well with the experimental results, especially after the vehicle. That was a nice finding to get that to kind of align directly. The profiles for U that are cross-cutting underneath the body are largely consistent with experiment up until the point we start getting into that the aft wheel interactional effects with the forward results. But all in all, I think the overall results are looking pretty good for solutions in this order using the meshes that we have on hand. Digging into the details a little bit more, so the A-pillar and side window being kind of historically challenging items to work through. One thing, we're catching the flow physics here quite well, some visualization of kind of all the eddies and structures. But I'll draw attention to this kind of like mid A-pillar region. So this collection of pressure ports all here in the mid-range, we have a really excellent agreement with experiment. So this is a positive finding. That's something we've perhaps had challenges with in the past years, but development is progressing in the right direction. So work on that is ongoing as always. And then the side window, overall, collectively, we're on the order of something like 10% differential with regards to the CP absolute values. Find that to be kind of acceptable for this particular resolution and time stepping. Also here now looking at wake comparisons with the experimental results. I really like this x equals 4 meters. So this is just downstream of the vehicle boot, and the as far as I can tell from a qualitative standpoint, those look very good to me. So happy about that. For the Z-plane cut that's going through the wheels, a little bit of deviation in our results, namely at this inboard station aft of the forward wheel. As well as the extent in which that wake kind of propagates downstream. The proximity to the ground plane, I think, is relatively tight here, so there may be some influential effects there in terms of how exactly the boundary layer mesh is resolved effectively for that relationship. That might be part of the influence, but otherwise, overall, globally, I think things look pretty good. Okay, so bring it to conclusions as the coffee break is coming up. So yeah, just some of the things that we talked about. Again, flexibility of Flow360. So we like to be able to work through fine-grained details, looking with DDES at the complexity of flow physics involved with some of these applications, but also while enabling rapid turnaround via RANS approaches, where that seems to fit in with industries looking to do those types of studies. The benefits that we're kind of talking about also are with regards to like adjustments to turbulence models, and as well as noting that the delta analyses show pretty good agreement from our expectations with experiment. The uniqueness of Flow360 is showing positive results also. So this is, as always, a great validation exercise, something we're always happy to be a part of these committees and workshops, because they do provide a great forum to test rigorously and learn from other participants and where points of challenges really happen to be. So yeah, for just an introduction to Flow360, come have a conversation with us. And I think with that, I'll close out and questions.